Because I remember it had a lot of things.
Me and also because both do sorry. I said it was an argument.
Or is it? Oh, really?
No, I said that's what
Oh, yeah.
Good morning, everyone. Good morning. Good morning. All right, let's get started. Okay, couple of things before we start. It is highly likely that we might have a snowstorm on Thursday. Good news, I guess. So it is also highly likely that on Friday morning I might end up seeing my driveway with half a foot of snow. If that is the situation, we are going to have class on Zoom. Okay? This is under extenuating circumstances only. And this qualifies as one. Alright? Thank you. If I can come to class, you will come to class. Okay, let's keep it that way. Alright. But I'll let you know on Thursday night. Watch out for my email on Thursday night. Wednesday, I think we're okay. We don't have any issues. So Thursday night, if there is a change, I will send you a Zoom link for the class, and we will have it over Zoom. Okay, just once or twice. Hopefully this semester, not more than that. Assuming we don't have a holiday on Friday. In my so many decades of being in Ohio State, I've seen maybe 2 snow days. So that tells you something. Alright, so we're going to go for a problem today, and then I'm going to continue on to radial systems. So here is a problem. Alright, so in this problem I have a wall, plain wall. One-dimensional heat transfer. And we are told that the side x is equal to 0 is insulated. So direction of heat transfer is along the x-axis. 1D. So this is insulated. Now we are told that there is positive energy generation within the body. So E dot G greater than 0, and for the sake of simplicity, I'm going to assume that E dot G is constant and uniform throughout the body. Okay? So E dot G is uniform throughout. But E dot G is switched on as soon as the time becomes greater than 0. Okay, so this is switched on. When t greater than 0, so which means that you are actually looking at an unsteady problem. We are not going to solve this, we are going to look at it qualitatively. Okay? And you are told that at t is equal to 0, at time t is equal to 0, the temperature of the right side of the wall, which is x is equal to L, and 0, this is at some temperature of 20 degrees Celsius. Okay? And you're told that the right side of the wall is exposed to ambient fluid. I'm just going to draw a small cloud. This is T infinity. Okay, so the ambient temperature always remains the same. It is not affected by the temperature distribution within the body, because ambient is considered to be much larger than the body. In the vicinity of the body, there could be some localized effects due to hydrodynamic boundary layer and thermal boundary layer. We will get to that at some point. Okay? So temperature T infinity is, let's say, 50 degrees Celsius. What we need to do is we need to plot temperature as a function of space and time for different time instances. Okay, so for 3 situations, some temperature T, time T is equal to T1, which is greater than the initial time. Okay, then for some, I'm going to call it as a special time. You'll see what the specialty is at that. This is greater than T1. So T suffix s is some special time. We don't know what it is. We'll get to know about it soon. And the third thing, when we reach steady state, which means that after a very long time has passed, what happens to the temperature distribution? T tending to infinity. Steady state. So for these 3 time instances, plot the temperature as a function of x and t. Plot or sketch. T at x comma t. Couple of things that we're going to assume in this problem, and you can have these kinds of assumptions as you see fit in your homework problems as well, or some other situations in real life applications too. We're going to assume 1D heat transfer. That's kind of expected. We're going to assume that the thermal conductivity is constant. Okay. Constant. In reality, the thermal conductivity can be a function of both temperature and space. Okay. And we are also going to assume that the volumetric heat generation is uniform, which I just wrote down, but I'll just write it again. So E dot G is positive at time greater than 0 and uniform. So it is not as if some pockets of regions in this body is seeing greater energy generation than some other pockets of this body. It's uniform throughout the body. Could be constant, could be something else, I don't know. We really don't want to know about it. Alright. So let's start off by looking at some time T1, which is right after the time has started, and the clock has started ticking, right after the energy generation has been switched on. Okay, so time T1 greater than 0, right after E dot G is switched on. So you can think that right after time is greater than 0, you're probably going to have some kind of a chemical reaction within the body. And this reaction is generating heat throughout the volume of this wall. Okay? So that's what this implies. Yes, question?
When we say generate heat, that's automatically Eg is greater than 0.
It could be heat generation which is negative, which is I could also use the thermal energy present within the body and remove that thermal energy to conduct a process. For example, an endothermic chemical reaction.
So the word generates.
The word generate can connotate both positive and negative. So you have to be careful. When I say there is heat generation, your question has to be, is it positive or negative? Okay, so which is why I have said that this is positive heat generation. Okay, so positive heat generation. Alright. So, what we're going to do is we're going to draw the system, okay, or the wall. And t is equal to t1, which is greater than 0. And you're going to tell me at the location x is equal to 0, what should be the slope? At the location x is equal to 0, what should be the slope? Should be 0, right? Because the side is always insulated. So no matter what I do, at whatever time I'm looking at, either is it at steady state or at the beginning of the problem, the left side of the wall will always see a 0 slope for the temperature gradient. Okay? So the slope is 0. Now what do you think is happening at the right side? Is it a 0 slope, a positive slope, or a negative slope?
It's not 0 for sure.
It's not 0 for sure, yes, that is true. So your choices are positive or negative. One of you had your hand up. Yeah.
I was going to say positive.
Positive, what's your reason for that?
Because it's generating heat, even though it's not a lot, it's still generating a little bit of heat.
Hang on to that thought, yes.
Heat generation is with respect to the derivative of the slope of temperature. So if heat generation is positive, our slope should be negative based on that equation.
That's very similar to what you suggested, yes.
I think it should be positive because the T infinity is greater than T.
I like that. I like that. You see, this is hotter than that, so obviously the direction of heat transfer has to be from the ambient to the wall. So we don't even need to think about the physicality of the slopes and so on from the point of view of the derivatives. Just a simple heat transfer. If something is hot and something is cold, the damn thing has to go from hot to cold. Okay? So if I draw the slope, obviously as you all mentioned, the slope is going to be positive, looking at it from x is equal to 0. Okay, so the slope here is positive. Some non-zero value of the slope, and then I join it as a smooth curve. Okay, so this is the temperature profile at T is equal to T1, so you call this as T at x, comma T1. Couple of things I want to point out. This is kind of cheating because we have really not solved the heat diffusion equation, the full-blown heat diffusion equation, which is including the time effects and the spatial effects. But what you will find out is that if you solve the one-dimensional heat diffusion equation, I'm just drawing some random temperature profile, you cannot have things of the sort happening. You cannot have things like this happening. And still a continuous curve. It's smooth and continuous, it is differentiable, C infinity and all that. But you cannot have something of that sort happening because of the nature of the solution that comes out from the heat diffusion equation. Neither can you have discontinuities within. You cannot have things like that as well, because the material is the same throughout the wall. The thermal conductivity is constant. It's not a function of temperature, it is not a function of the spatial position as well, so I cannot have physical discontinuities in a temperature profile. So none of these situations will arise in problems for us where the thermal conductivity is a constant for a given wall. And you want to be careful. If I have two materials, dissimilar materials, which are in contact with each other, at the junction of the dissimilar materials, I can have discontinuity in the slope. Okay? Yes, sir.
If heat generation was dependent on position, if we see graphs,
You could see graphs that look like something of this sort, or if your thermal conductivity is a function of position as well. But you cannot, typically these things don't take place unless you have different thermal conductivities, different materials within the same wall. Okay, which you will have in your first homework problem next week. Alright. So this is the temperature profile for us. This is at time t is equal to T1. And you can obviously see if you perform an energy balance, okay, if I draw a control surface around the entire wall, this side is insulated, so there is no heat transfer going in or coming out. From the other side, I have heat transfer coming in, so energy transferred in the form of heat. I have positive energy generation taking place. E dot G is greater than 0. So which means that if I write the energy balance equation of the first law, E dot store, E dot in, E dot out. Mind you, we have positive energy generation, so that is plus E dot G. This is 0. Don't have anything going out of the other side. This is positive. This is also positive. So at the beginning of time, my rate of change of stored energy is going to be positive, which tells me that my temperature of the wall is going to increase with time. Okay, so here I am essentially seeing the E dot stored is greater than 0. So at the next time instant, this situation will continue. Maybe the slope at x is equal to L will be a little lesser in magnitude, because you see that the temperature on the left side of the right side of the wall has now increased a little more than before, but I'll still continue having this profile for some time. Okay, so maybe next instant in time, a slightly lesser slope at x is equal to L. Okay. Now, we will reach a time, Ts, I call it as a special time, because what do you think is going to happen to the right side of the wall? X is equal to L. What do you think is going to happen to that side? It's getting hotter. Can it keep getting hotter infinitely? Yes?
I was going to say it's going to reach T infinity.
It's going to reach T infinity at some point in time. That's the special time I'm talking about. When the right side of the wall reaches T infinity. And T at x is equal to L is equal to T infinity. This is suffix Ts here. T at x is equal to 0 is still going to be constant. There is, it's some temperature, I don't know what it is. But the slope is going to be 0 there, because there is still no heat transfer across that surface. It's insulated at all points in time. If I say that this is equal to T infinity, then what should be the slope? If I draw this wall creature, this is at T is equal to Ts. What should be the slope on the x is equal to 0 side? Same as before. What should be the slope at the x is equal to L side?
0.
Should also be 0. And so at this special time, my temperature is going to be the same throughout. This is the x is equal to 0 side, x is equal to L side. And because of the fact that we are assuming uniform volumetric energy generation, we are assuming the thermal conductivity is a constant, I cannot have funky things like that taking place within the material. I cannot have discontinuities within the wall. Okay, so this is what is going to happen at both these wall locations. So this is also no heat transfer. This is no heat transfer. So the slope is 0 at both locations. What about my first law? E dot in, E dot out, E dot generated. At this instant in time, there is no heat coming in, there is no heat going out, so E dot in and E dot out are both 0. But E dot G is still non-zero and positive, so the temperature of this wall is still increasing with time. Okay? E dot stored is still greater than 0. Then we go to steady state. What is E dot stored at steady state? 0. right? Because that is the definition of what a steady state is for us. This is at t tending to infinity. If I now draw the profile, before that this is t as x and t suffix s. And what you'll figure out, we will not be doing this in this course, it falls beyond the scope of this course. You can solve the one-dimensional heat diffusion equation. Okay, so you can solve this equation is some q dot plus k times d square t by dx square. One can solve this equation. A common solution for this equation is called as the Ogata-Banks solution. And for the kind of assumptions that we have in our problem, where the thermal conductivity is a constant and you have volumetric heat generation that is uniform, for a given time, you will find out, if you look at the solution, and I'll post the solution, we won't be looking at it of course, I'll post the solution. At a given time, the temperature profile will be a combination of an error function and an exponential curve. So it will look like the sort that we have drawn here. It will not look like this guy. Okay? Once again, this is beyond what we are doing. Okay? Alright, now I go to the third situation, steady state. Easy here. Zero slope. What do you think happens at the x is equal to L side? This is x is equal to 0, x is equal to L. Remember, as time is increasing, the energy stored is still greater than 0, so the temperature has been increasing. So what's going to happen at the x is equal to L side? There is going to be heat transfer taking place from the x is equal to L side onto the ambient, because we are now seeing that the x is equal to L side exceeds the ambient temperature. Okay, so the slope here is going to be negative. The slope at the x is equal to 0 side is 0, and we have a nice smooth curve. Okay, and so there is heat transfer out. If I draw a control volume, control surface around this body, there is E dot out. E dot generated is 0. E dot stored is 0. I'm sorry, because we are at steady state. This is t at x, and as t tends to 0, if you perform your energy balance, this is your typical situation. E dot out will end up being equal to the energy generated. Okay? And because of the fact that there is some heat transfer going on from the wall onto the ambient, the temperature at this side is obviously going to be lesser than the temperature there. Okay? So these are the three situations, and you can draw them all in the same plot, which I'll do here. This is the first situation when t was equal to t1, so this is t at x and then t1. Then I have the special time t suffix s, where everything is now the same temperature. And then as time goes on, this guy starts mirroring its image or behavior, and then I'm going to have something of this sort. This is t at x and steady state. And the moral of the story is that you don't need to know how to solve these kinds of complicated equations to understand how qualitatively the temperature changes as a function of time. And of course, one can solve this. This is not very difficult to solve. One dimension is not very difficult to solve. 2D, you need to do numerical techniques. Closed form solutions are very rare. And for different characteristics of heat generation, the problem becomes more and more challenging. For different functional dependencies of the thermal conductivity, it becomes much more messy. So numerical solutions are the way to go. Alright, so this was a small digression from where we were in the last lecture, where I started my radial system heat transfer. Yes, question.
So in the third case, will the surroundings be heated to more than 50 degrees Celsius?
No, the surrounding temperature you assume is always like a bulk temperature. It is not going to change as much. You will see that there will be some wall effects which are taking place right there in the vicinity. But on an average, it's almost like taking a bucket of hot water and pouring it into the ocean. The ocean temperature doesn't change. So something similar to that. Or having a bucket of hot water close to the ocean. Alright. So which is why we call it as a bulk temperature. But there is still heat transfer taking place. That cannot be changed. Okay, so moving on. We started radial systems last time. I want to develop the theory behind it a little more. And then we want to look at some very strange type of problems. Okay? The radial systems. Cylindrical, spherical, and so on. Once again, 1D. The direction of heat transfer is in the radial direction for us. Right, so if this is the situation, then the surface area, and why are we interested in radial heat transfer is if you look at pipes. The largest exposed area for heat transfer is along the length of the pipes because the pipes run a very long length. Typically their diameters are small, and so there will not be much circumferential heat transfer. There will not be as much axial heat transfer. The maximum heat transfer takes place in the direction of the longest dimension in that sense. So the radial heat transfer is the maximum for us. That is normal to the direction of the longest dimension. That's where the direction of maximum heat transfer is. And we said that the surface area, if we consider a cylindrical pipe, 2 pi r times L, where L is the length of the pipe. And this is some radial distance r, okay? This could be at the outer radius r0 or inner radius. So I could talk about an inner and an outer radius. And the issue here, as opposed to what we saw in a plane wall, is that now the area is a function of the radius. For a plane wall, the area was a constant for one-dimensional heat transfer that we used to look at. Okay? I set up the following figure last time. Solid body. We're going to assume thermal conductivity is a constant. Then we're going to have volumetric heat generation. So this could be plus or minus. Now I don't know. Okay. It depends on the problem, the nature of what we are given. We could have some unsteady effects. This is not 0. This is also not 0. And what we decided to do was we decided to draw a small control volume, which I'm going to show here. Right, so that's our control volume. And if I draw a two-dimensional view of that, here is the situation. I'm going to say that the thickness of this volume element is delta R. So this is delta R. Then I'm going to say that the radius at the inner ring, this is almost like a cylindrical shell, radius at the inner ring is R, which means that the radius of the outer ring of this volume element is R plus delta R. R plus delta R. And we are going to say that heat transfer is taking place starting from the location R is equal to R and going out at the location R plus delta R. Okay, so if I look at the direction of heat transfer, it's all radial. Coming out and this is Q at R plus delta R. And this guy is Q at R, where Q is the rate of heat transfer. Please remember, thermodynamics, you had Q dot. We are not using that symbol here. We are using just Q. Q is rate of heat transfer for us. Q dot has a different meaning in heat transfer. It's volumetric heat generation or energy generation. And that is unfortunately as a consequence of using different textbooks for different courses. Okay, this is not by my design. Not my desire either. Alright, so with all this said and done, we will look at the derivation very quickly. And we also discussed the following last time. If I look at the volumetric energy generation term, E dot G, we wrote this as Q dot times delta V, which is Q dot times area times delta R, where the area A could be written as 2 pi RL using the inner ring radius, or you could use the outer ring radius, but in the limit of delta R tending to 0, those small terms or higher order terms will essentially drop off. Okay? So for us, we will assume this to be the case. This is approximately true for an infinitesimal ring. And we do something similar to what we did for one-dimensional heat diffusion equation for plane walls. I start off by writing the energy balance using the first one. E dot stored, E dot in, E dot out, plus or minus E dot generated. For the time being, just assume that Q dot is greater than 0, so maybe let me write that down. So say Q dot is greater than 0. Can also have Q dot less than 0, in which case it comes with a negative sign. Okay, so no big difference. E dot stored is mass times specific heat times the change in the temperature with respect to a reference temperature at two different time instances. So T at some R, function of R, T plus delta T minus T at R and T. Because it is a rate of change of stored energy, it has to be divided by delta T. This is what I have on the left hand side. Mass, we write it as density times volume. So with your permission, this is going to be rho times A times delta R. Okay, where I have substituted for mass as density times volume, and volume is area times the thickness. Okay, this is equal to E dot generated, which we write as Q dot times A times delta R. E dot in is the rate of heat transfer into the control surface, and E dot out is the rate of heat transfer out of the control surface, which is Q at R and Q at R plus delta R. This is Q at R. R plus delta R, where Q is the rate of heat transfer. So this will be in watts. One more assumption that we are making in many of these problems is we are not including any work interactions. So there is no shaft work involved, there is no paddle work, there is no PDV work, and so on. We will look at problems that involve work transfer very soon. We will take it step by step. I do the following: divide through by the area, divide through by delta R, which will give me the following. So I have rho C R and T plus delta T divided by delta T. So I divided through by A and I divided through by R. So these two terms vanish here. They vanish in the Q dot term as well. So this is equal to Q dot. Now watch this. Q at R and Q at R plus delta R, I switch it around, put a negative sign. I take the delta R, write it with the Q of R terms. I have to divide through by the area A as well, so I did that too. And I take the limit on both sides. Limit delta T tending to 0. Limit delta R tending to 0 on both sides. And in the limit of very, very small infinitesimal time, in the limit of an infinitesimal ring element, these terms become partial derivatives. Why partial derivatives? Is because they are a function of time and position. Okay, so here I have rho times C dt by dt. T is a function of R and T. This is equal to Q dot, which does not undergo anything, minus 1 by A times d by dr of Q. Now QR is once again the rate of heat transfer, which according to Fourier's law is the flux times the area. And if I write that out, Q of R is minus K times A times that. This is from Fourier's law. Which means you are now going to do the substitution. So be careful, in the plane wall situation, I did not have an area term coming into play. I looked at only the conductive flux terms. Reason being, the area is constant. The area for heat transfer in a plane wall is always constant. That's not the case anymore. You see, because the area is a function of the radius r. So now we are going to do the following. Substitute. For QR, don't get rid of the area yet. So rho times C dt by dr, dt by dt, I'm sorry. Is Q dot. I have a negative sign 1 by A times dq by dr, but Q of R itself has a negative sign because it's proportional to the negative temperature gradient, so it becomes positive 1 by A d by dr of K times A times dt by dt. And now this is the most general one-dimensional heat diffusion equation. Look at this. Plane wall, area is a constant. And so you can get rid of the area terms 1 by A and the A, which is within this derivative here. So I can get rid of these two terms in the plane wall situation. And if I say that R is the same as X, usually for one-dimensional plane wall situations, we assume X as the variable of interest, you will end up with your regular equation. Is Q dot and K times d square T by dx square. All I'm doing is substituting R as equal to X. This is for a plane wall. Second situation, if I have a cylindrical body, the surface area available for heat transfer at some radius r is 2 pi r times L. If I do the substitution into my heat diffusion equation, I end up getting the following. So this is going to be rho c dt by dt q dot area 1 by 2 pi rl d by dr k times a is k times 2 pi rl dt by dr. So far so good. Cancel of the 2 pi, cancel of the 2 pi, they are physical constants. The length of the cylinder is also a physical dimension that does not change as the cylinder undergoes heat transfer. But I cannot do the following. I cannot cancel off the r here and the r there. Okay, because this is within the derivative. So if I write my final answer for a cylindrical wall, cylindrical body, I will have rho times c dt by dt. K is a constant thermal conductivity for us, so I will say this is q dot plus k by r d by dr of r dt by dr. Spherical body. Very quickly, I'm not going to do the derivation, you can do it at your free time. If I have a sphere, what's the surface area? Archimedes came up with this very nice theorem. The surface area of a sphere is the same as the surface area of a cylinder whose height is equal to the diameter of the sphere. Okay, so I'm going to write that down here. So surface area of a sphere is the surface area of a cylinder, which is 2 pi r, with the diameter of the cylinder being the same, the height of the cylinder being the same as the diameter of the sphere, so that's 2 times r, which is 4 pi r square. Okay, so this is the number 2, Roman Arabic letter 2 here. So 4 pi r square. If you do the substitution into the main heat diffusion equation that we have derived, not going to do that, you'll get the following. Rho c dt by dt is q dot plus constant thermal conductivity, assuming k by r square d by dr r square dt by dr. And now I'm going to do the following. Okay, this is cheating, but I can do it. Rho c dt by dt, going back to the plane wall, is q dot. I'm saying r is the same as x, so instead of x I'll write it in terms of r, plus k by r to the power 0 d by dr of r to the power 0 dt by dr. Yes, sir, question.
This is only assuming that k is constant.
Absolutely, absolutely. This is only for the situation that k is a constant, so k is a constant. It's not a function of position, it's not a function of temperature. And this is a very valid assumption for a majority of the bodies that we study. Okay? This is not like something wrong, it is completely fine. You see what I've done here? R to the power 0 is 1. So 1 by 1 is hopefully 1. R to the power 0 here is also 1, so it does not change the nature of what I've done. Come here and see, this is r to the power 1, r to the power 1. So if I have a cylinder, instead of r to the power 0, I just switch it and write it as r to the power 1. If I have a sphere, it's r square and r square. And so if I have a general one-dimensional heat transfer situation, in general, one d k is equal to constant. Here is my equation. Rho times c dt by dt is q dot plus k by r to the power n d by dr r to the power n dt by dr, where if I have a plane wall, n is equal to 0, r is the same as x. Cylinder, n is equal to 1. I have a sphere, n is equal to 2. And this little creature here packs so much punch. Just by knowing one equation, I know the behavior of 3 different bodies. Okay? All right. So our focus is going to be on cylindrical bodies because of pipe flows and so on. As engineers, we are always interested in that. Hot fluid flowing through a pipe. The pipe has a certain thickness. Conductive heat transfer through the thickness due to convection at the surface of the inner surface of the pipe. Outer surface of the pipe could be exposed to ambient, so there is convection there as well. If you don't want the rate of heat transfer to be too high, you just put an insulating ring around the pipe. What's the thickness of this insulating ring? That's something that we need to figure out. And so that's where we are slowly heading towards. The most practical problem that a heat transfer engineer can know. What is the thickness of the layer of insulation I need to put around this particular pipe, given the following conditions? Okay? Very common interview question too. You can cite me on that. All right. But before doing that, look at a solid cylinder. How does heat transfer take place in a solid cylinder? Start with the heat diffusion equation. And I'm going to say K is constant. I'm going to look at a situation of constant volumetric energy generation. So E dot G, which is Q dot times the volume is a constant. Could be positive or negative, I don't know. But let us assume it to be constant. So Q dot is constant. Write the heat diffusion equation for steady state. Rho times C dt by dt is gone. This is equal to Q dot K by R d by dr or dt by dr. This is just a general equation that we've derived. I'm going to write it down. Steady state dt by dt is 0. I want to come up with a temperature profile. Q dot is a constant. So take the terms, rearrange them on the other side. K is a constant. So I have K by R or dt by dr is minus Q dot. Take the K by R, flip it onto the other side. Becomes an R by K. integrate both sides with respect to r. I lose one of the derivatives on the left hand side. On the right hand side, if I have a function of r, it becomes a next higher power of r. So this is going to be r times dt by dr. I lose the first d by dr term. This is now going to be minus q dot r square by 2k plus a constant c, which we do not know yet. Okay, bear with me for a few more minutes. Now I can take this r on the left hand side and spread it out. So if I take this r, I get a bar. Okay, so I don't have an r on the left hand side, I'm just taking it out, cancelling off one of them from the r square, and then c1 becomes a c1 divided by r. Then integrate one more time. So now I have dt by dr is minus q dot r by 2k c1 divided by r. Okay? Integrate one more time, both sides. T of r, q dot constant, 2 is a constant, hopefully k is a constant given to you in the problem, a function of r, so it becomes r square. Instead of 2, because I am integrating r, I get another factor of 2, so this is 4k. What is the integral of 1 by r dr? Natural log of r, yeah, there's not much thinking to do. Plus c2. Now we have hit a roadblock. Because I have a solid cylinder, right? That is the starting point here. Do you all agree with me that if I take a solid cylinder and I measure the temperature of the cylinder at r is equal to 0, it should give me a physical value? Right? If it is hot, it should give me a physical value. But if I substitute r is equal to 0 here, what happens to this guy? What is the logarithm, natural logarithm of 0?
Doesn't exist.
Does not exist. It is not physically possible. And so, by sleight of hand, we say, okay, if you have a solid cylinder, this is mind you for a solid cylinder, if you have a solid cylinder, because of the fact that the temperature at the center of the cylinder is a physical quantity, but because of the fact that the logarithm of 0 is not defined, I'm going to take that creature out and throw him out of my life. And so if I have a solid cylinder, is a physical quantity. So which tells me that T of R for a solid cylinder minus q dot r square by 4k plus c2, and this tells me that if I take the derivative of T at r is equal to 0, this derivative will end up being equal to 0. And this is called as the symmetry boundary condition, which tells you that the center line of a cylinder is always insulated. It's an isothermal surface, temperature is constant throughout the length of the cylinder, but it's also insulated. Okay, so this is a symmetry boundary condition, which tells us that the center line is insulated. This is for a solid cylinder only, please. Yes, question.
And that's because our heat transfer is in the radial direction, not the length.
Absolutely, because if it was in length, the heat diffusion equation would have changed. That would have become a two-dimensional one. So we can't solve it using this technique. All right, thank you.